Swayam Prabha. Digital India. Educated India.
So, we are discussing about instabilities for blood body flows, and one of the redeeming feature of this particular flow is here you see temporal instability, right, quite unlike streamlined bodies we had discussed so far, where we mostly confined ourselves to spatial instabilities. Let me just show you one of the figures that we saw in the introductory part of the course, where we showed you some results, experimental results conducted here in one of our tunnel. What we were interested in studying is the role of background disturbances on instabilities. So, in the context of temporal instability, it is rather important to see that how background disturbances affect flow instabilities. What we did is we kept the Reynolds number and a post critical value, something like 53, which is quite compatible with the background noise that is prevalent in the tunnel. This Reynolds number were achieved for two cylinders of two different diameter, one with 5 mm diameter, the other one is 1.8 mm diameter. The reason that this is a higher diameter cylinder allows you to run the experiment at a very smaller tunnel speed of 17 centimeter per second. When you reduce the diameter, you run it at 46.9 centimeter per second. So, if I now try to sort of do an analysis of what has gone on and compare these two experimental results, what we did was we removed the models and run the tunnel without any model at those speeds 17 centimeter per second and 47 centimeter per second, and obtained a time series. It is simply a hot wet race, and then you can do a fast Fourier transform, so that you can find out the spectrum of the noise in the tunnel. So, what we have shown is the amplitude versus frequency of the noise, and what we know also from lots of experiments that have been done over the years. People have collected the data, and they found out what is the Strual number, the characteristic frequency of flow past a cylinder for this Reynolds number. So, the Strual number is quite a given quantity. So, what we did was try to find out what is the magnitude of the disturbance at the Strual number, and for this lower speed you can see that is the peak. The peak corresponds to the Strual number, and there we see the amplitude is roughly about more than 2. Okay. Whereas, when we did this experiment at a higher speed of 47 centimeter per second, and we tried to find out what is the amplitude at Strual frequency, and that has been zoomed here in this inset, and you can see that value is about 1/10 than this, and that difference of background disturbance is very clearly revealed in the wake pattern of these two flows. In this case, you can see very clearly well defined wake vortices typical of Karman-Venard vortex treat, whereas what do you see here? You see a kind of a attached bubble. This is something that we were also talking about, the experiment done by Fritz Hohmann. What was done in that experiment was we mentioned that a lubricating oil was used as a working medium. There also a similar flow feature were observed. It is something like this, that if I take a flow past a cylinder, then what happens is, as I keep increasing the time, I mean if I am solving the Navier-Stokes equation and if I am doing the experiment also, perhaps I will see it, but far too rapidly. In computing we can see it in much more better way, we can visualize it. What happens is, initially you see a sort of a symmetric bubble forms. That bubble keeps growing with time, and after quite some time the bubble takes some kind of equilibrium form. But then what happens is, if it is a post critical Reynolds number, then what happens is one of the bubble starts growing asymmetrically with respect to the other, and when it grows in sufficient strength, that side is the vortex is shed from that side, while this one gets emaciated while that was growing. But then now the cycle reverses, this one starts growing and that remains quiescent, and this is what you are seeing here. Okay. However, if I now have a flow which is kind of noisy, but not to the great extent, that is what is characterized by free stream turbulence, right. So, this noise is kind of flat across a large frequency, there is no preferential larger value at that. So, this is what you are seeing is basically the receptivity aspect, that if I have a disturbance at the Strouhal frequency, I see the Kalman vortex trait. If I do not have, then I get this. Now, this flows also have large eddies like this, right. So, what happens is, this is what? This is a shear layer, this is a shear layer. If I look at it, outside the streamline could be like this, and inside I have a recirculating bubble, and that might be going like this. And if I look at this interface, now this interface is interesting. This is something which we have studied, where the Kelvin-Helmholtz instability, right. We studied that, and what we found in Kelvin-Helmholtz instability is that if I have the velocity in the opposite direction, that tends to destabilize. So, here also the same thing can happen, that while the computation in the absence of any noise done with very good quality numerical methods will show this kind of a steady periphery of the bubble. However, because of this presence of these disturbances, that interface develops a Kelvin-Helmholtz instability, and those Kelvin-Helmholtz instabilities will cause some of this vortices to be stripped off from this. And so, what you see is essentially some kind of a weaker eddies of this kind. So, please do not confuse by saying, okay, this is a Kalman vortex trait, this is a weaker form of Kalman vortex trait. It is entirely a different phenomenon altogether. The origin here was alternate shading right from the surface, whereas this picture corresponds to the case where vortices are stripped due to Kelvin-Helmholtz instability from this wake bubble. Okay. Now, if you go back and look at those results, those were shown by in Fritz Homann's case, something that I would like you to take a look at. There you would see that even the results, those are produced for 65, there you would have seen that this is more this kind. You have a attached bubble at the end, and the end of the bubble is fluctuating and creating undulating wake. So, this is not like what we would say in the classical sense, the Kalman vortex shading. Now, when you do have Karman vortex shedding, to explain that, we in the last class we talked about the development of Landau equation, and this was the evolution equation for the amplitude, and this is the evolution equation for the phase angle. So, that actually will give you a sort of a frequency of shedding, and this frequency of shedding is rather interesting, because what it shows that this frequency of shedding of the nonlinear dynamical system is equal to what is given by the linear system modified by this part, and this part has come about from the Landau equation, and what it shows that this frequency is proportional to the amplitude. That is an important thing, one of the important aspect of nonlinearity, amplitude dependence, right. And of course, it also depends on the imaginary part of the Landau coefficient, right. Now, if I look at the amplitude evolution equation, what I can do is I can study an equilibrium state. So, equilibrium state of 5.17 is what? That would be given by when I put the time rate equal to 0, isn't it? And that is what we figured out. So, that would be this 2 sigma r mod a square minus L r like this. So, this corresponds to equilibrium state. So, I will write it as E. And this of course gives you two sets of condition. So, one of the condition is of course this, and the other condition is given here, that is equal to A e equal to square root of right. And so, what I could do is I could plot on this side R e, and on this side I can plot A e. How should I see the variation? This comes from the linear instability path. Okay. What have we? For linear instability, what I find that in the post critical case, it goes as some k times R e minus R e critical, right. So, if I do that, what does this tell us? This tells us A e goes. So, one of the solution is A equal to 0. So, that could go on here, one branch of the solution. The other branch would be starting from R e critical, and that will be a parabola, right. And we said that this is your Hopf bifurcation. You can have two state. This is a beautiful simple example of Hopf bifurcation, where beyond the critical Reynolds number you can have two state, either this or this. So, what we just now seen in the experiment, this would not be revealed from this picture, that the Kelvin-Helmholtz instability path is not given by what we have been talking about in this case. That is where we figured out that equilibrium amplitude is something different than what we are talking about. This is strictly about Kalman vortex threading, right. So, please do keep that in mind. Okay, so, here we have it, that we have seen truly the effect of nonlinearity. Also, I would like to reiterate that this case that we are talking about, we are talking about the cases for which LR greater than 0. This is typical of blob body flows. Okay. We have similarly a case of LR less than 0. This you actually see in Poisson flow, or channel flow. What do you notice here? You notice that that in this case we will not be spending time, but I am just simply mentioning the fact that if LR is negative, what the nonlinearity does here? It actually increases the instability, because the time rate of change of amplitude is augmented by this term. So, that is what was the whole intention of Landau in proposing this equation, that it can explain supercritical stability. That is what it is doing, right. The nonlinearity is causing a stable, helping you get a stable amplitude, and that is your Kalman vortex shedding. Whereas, if I look at plane Poisson flow, LR is negative, and there we can talk about subcritical instability, right. So, this Landau equation is quite a nice model equation to explain both. So, we have talked about all of this. So, there is nothing much that we need to add to that. We did also talk about the equilibrium amplitude as given there, we have shown it. So, we could talk about an equilibrium Strouhal number. You know, there were lots of attempts in 70s and 80s. People have spoken about describing this nonlinear action in blob body flow instability by measuring Strouhal number. It is an easy thing to measure, right, because unlike the amplitude, you will have to put in a probe, and I told you about Kovasner's experiment in late 40s. When he put in a hot wire probe, he saw the vortex shedding disappeared. We talked about that subsequent work done by Strykovsky and Srinivasan, which investigated that putting in a smaller cylinder in the wake of a large cylinder and controlling the vortex shedding completely for a Reynolds number less than 120. It was shown experimentally late 80s. However, that started with the original observation by Kovasner. When he put in a probe in the wake of a cylinder, the wake pattern changes. So, basically to understand this nonlinear action by putting in a probe and measuring is rather difficult, but if I put it far downstream, because Strykovsky and Srinivasan map the region where you have to put this control cylinder. So, if I put it beyond that region, then I can get it, then I can study the wake. Problem is two. One is, of course, the amplitude is too low. So, you would not know with reliability what is it that you are studying. And the second thing is about it is much easier to measure the frequency. I will get the oscillation, and once I have the time trace, I can do a Fourier transform and I can obtain the Strouhal number. So, this is what we are talking about. The Strouhal number is the equilibrium Strouhal number from the other equation, and that equation was what? that equation was omega equilibrium should be equal to what you get by the linear theory, and this was Li by 2, and this is that, right. So, now one can collect the data, and a lot of people in fact emphasize on this aspect. Now, this is something that we need to really talk about, that earlier numerical investigations by various groups identified the vortex shedding at a critical Reynolds number of 45 and 46, but this was indeed not the case that we reported off with respect to Hohmann's experiment, and we did talk about all of this, the whole range of values experimentally produced, and this is what it is. The tunnel experiment that I showed you beginning of this lecture, on that particular tunnel I think you can even get vortex shedding at a Reynolds number as low as 40. So, there is no need to really think anything particularly about this particular work. This is a completely a theoretical approach, pedagogic approach, strongly dependent upon the numerical method that they have chosen. And what we talk about then when we look at the experiment done by Fritz Hohmann, that does not display this Re critical 1. This value we are talking about Re critical 1, the first Hopf bifurcation. Okay. Instead, Hohmann's experiment identified a critical Reynolds number somewhere here, which is far in excess of what this is. So, if this is about between 45 and 46, this is about 65 or so. So, that is what we are talking about as Re critical 2. Now, basically you should view those computations reported by Jackson, Jebiv and Morzinski-Thiele as one which basically talks about the transfer function of the dynamical system. That shows this Re critical 1. Now, the experiment that we saw is a case where the system is ready, but the input is not there. That is what we showed by showing that empty tunnel noise. And then you do see a different scenario altogether. So, it may so happen that if I do these experiments, measure the critical amplitude versus Re, people have noticed, I do not know whether I have a view graph for you to see that, but this is quoting from the experimental result of Strykovsky's thesis, PhD thesis. It is noted that it has something like this. This you do not have a parabola. So, you have a kind of a parabola here, and you do tend to have, let us say, another parabola here. And this kind of a scenario where you may have bifurcation at Re critical 1 and again a virtual bifurcation at Re critical 2 is what you see actually in experiments. That is what was shown in Strykovsky's thesis experimentally. So, what one can talk about is the following, that in Hohmann's experiment, the use of highly viscous liquid stops the flow of the background disturbance altogether. So, you do not get this. The first critical Reynolds number is bypassed, Instead, you go to a higher value of Re critical, where the flow is susceptible to even smaller levels of disturbance, and that gives rise to that. Okay. Now, when it comes to numerical error computation, one must also understand that you have to develop numerical methods which faithfully follows the physical dispersion relation. Most of the cases when it is not done with care, numerical solutions are laced with dispersion error, okay? And that can really alter the flow dynamics qualitatively. And we did look at these issues and develop numerical methods. And in this particular work, well, I think it's not here. There was this particular work where we tried to reproduce that flow control experiment of Tchaikovsky and Srinivasan. That is what we were saying, that by putting in a small control cylinder in the wake, they could delay vortex shading all the way up to Reynolds number of 120. And the flow was nominally 2-dimensional. There were some computational results produced here, but I suppose this was where the most recent and more reliable results reside. We computed this flow, including the actual geometry, unlike what was done in Tchaikovsky and Srinivasan, where they had difficulty with grid generation and the method was less reliable in that sense, that you did not simulate the control cylinder. Instead, you took a cluster of points where you put an equivalent effect of putting some body there. So, that was more like a modeling effect. And in this particular paper in Journal of Fluid Mechanics, we did show what was reported experimentally, and that is basically a testimony of developing numerical methods which are more correct. And this we did show that if we compute the flow for a circular cylinder at R equal to 100, this is how we see it. This is how we see it, that initially we do not have shedding, and the CL lift coefficient remains more or less flat, barring this very high frequency oscillations that you see in CL versus time plot. That is seen even better if you plot the drag coefficient versus time. Those fluctuations are present here too. And what happens is, despite those high frequency fluctuations, the flow remains kind of insensitive. After some time, slowly you start seeing this instability as given by linear theory picking up. Okay? And these are the ones, this initial exponential growth is governed by the linear instability, and this nonlinear saturation is quite nicely modeled by Landau equation, right? And the drag coefficient actually initially after the transient reduces, then again it increases. Please understand this is done in a negative scale. So, the drag increases, and then we have the drag variation also gives a kind of a frequency which is not same as the frequency for the lift. Why? Because in each cycle, complete cycle, the lift varies, right? Whereas in each half of the cycle, the drag keeps varying too. So, what will happen is the drag variation frequency will be twice the frequency that you see in lift, right? So, think about it again, right? Why would you do that? Why would you see that? Because the full cycle gives you a 1 Kalman vortex shedding, but in that full cycle also the drag varies. Drag varies about its mean, and so that is why this frequency is twice than this frequency. Okay. So, this was a post critical Reynolds number calculation result, and we have already talked about this dispersion relation preservation method, which we have used, and we should actually use all these dispersion relation preservation methods in studying instability problems, because we have by now convinced that instabilities are governed by the dispersion relation. So, our numerical dispersion relation should match physical dispersion relation. This is quite a must. Okay. Let us look at the solution of that evolution equation for the amplitude that we have gotten. This is what we have written. I suppose this was the reason that Landau was particularly interested in this model, because AE we have shown here is like this. So, in that ordinary differential equation, although you have an equation for a square, but there is a to the power 4 term. So, it is a nonlinear equation. Despite that, it admits exact solution, and that solution is given here, and A naught represents the value of A at t equal to 0, okay? And AE is as given here. So, there is no such problem. So, you get the time variation like this. Now, in a post critical scenario, of course, sigma r is positive. So, with time this is going to decay, right, e to the power minus 2 sigma r t. So, for a very large time, what will happen? This part will cancel out, and what will happen? This a naught square will cancel out, and a square goes upstairs, and that is exactly what we saw in the figure, that you achieve a equilibrium state. Okay. So, this is the beauty of Landau's equation. And in the bottom we talked about that while Landau himself paid all his attention on the amplitude equation, and he claimed that the phase is indeterminate, which is not true. We have seen the phase is given by this, and that is that equation, right. And as A approaches its asymptotic value A e, the circular frequency actually comes out like this. It is interesting what you notice, that the equilibrium amplitude is totally determined by the linear stability property. That is what it is, right. Sigma r plus I omega is the linear exponent, but it also depends on the Landau coefficient alone. Again, this is interesting, because this Landau coefficient does not depend on the initial condition, right. It is again a system property. So, although we wrote earlier in terms of like this, but now suppose I replace A square by what we have there, that will be 2 sigma r by L r, then we are seeing that relation, right. So, it shows that it is totally determined by the system dynamics, does not depend on amplitude. Unfortunately, though, lots of experimental investigation has been carried out thinking that this true Hall frequency is a function of amplitude, which is not true. By the way, there was this experiment done by a French group in 80s, Provençal, Mathis and Boyd. What they did was they did a similar experiment like what we shown here for r equal to 53. They took 3 different cylinders in the same tunnel, and they found different critical Reynolds number for different cylinders, and they attributed it to 3-dimensional effect. There was this systematic study done by Williamson in 80s, CHK Williamson, And Williamson has written lots and lots of review paper on this topic. If you look at annual review of fluid mechanics over last 20 years, you will see at least 2 or 3 such review paper written by Williamson. And Williamson has demonstrated experimentally by doing very careful experiment that 3-dimensional effect, instability effects shows up for a Reynolds number which is above something like 180, 200 in that range. So, Provençal and his groups reporting of critical Reynolds number for 3 different cylinders giving 3 values all less than 100 implies what? Implies what we talked about, because they were doing the experiment in the same tunnel, different cylinders, but they are doing at different flow speed. See, this is something very amazing, that even today if you look at many experimental results, people talk about free stream turbulence of a tunnel as if it is a fixed albatross hanging around the neck of the tunnel. It is not so. This free stream turbulence is a property which has a spectrum, and this spectrum keeps changing with the operating condition. So, this is what we are trying to emphasize over the last few years, that please do take a look at the spectrum, and you will see that the spectrum keeps changing with speed, and that is exactly what Provençal's group also did. And that was another sort of a supporting evidence where you could see the effect of noise, the spectrum. Now, instead of using this equation that we have written here, it was Koch, Werner Koch, who suggested that Strual number is given by what you get from the linear instability. The system latches on to the linear instability mode. Okay, proposed a kind of a resonance, and that is more or less correct, right? That is what we also seen, that at the Strual frequency, if I have a large enough amplitude, we will get that, right. So, that is something we need to understand, that the Strual number is related to what you get out of linear instability, right. So, let us understand what Koch was essentially trying to say. This is important because we need to understand what really happens in a flow like this, in a blob body flow. See, when we saw the flow past a flat plate, what happened? We created a fixed frequency excitation at a point, and then it created all those waves which convected downstream. We called it a convective instability. What happens in the wake of a cylinder? This has been perplexing people for a long time, that if I put in a probe here somewhere in the wake, then I will see the signal increasing with time. So, there is a space very near to the wake of the cylinder where we see temporal instability. That means where the disturbance grows with time. Once it grows with time, that gives rise to formation of this separation bubble, the recirculating wake, and we have nonlinear saturation that takes us to the equilibrium state. But that equilibrium state gives rise to this vortex shading, that is perfectly fine. But once the vortex is shed, what does it do? It convects away. So, this is what people have been talking about, that you must have some location in the wake, okay, where the linear instability is predominant, and that is fixing your Strual number. Note that earlier Nishioka and Shato, they also have come to a similar point of view. They say that if you are looking at this particular location, flow is absolutely unstable. What is absolute instability? Absolute instability here is something like you are located at a fixed location and the disturbances are growing in all directions. That is something like your temporal instability also. So, there has been a kind of a, I would say, a model thinking in the field where people have interchangeably used the word absolute instability versus temporal instability. So, if I have a temporal instability, well, it is there at a fixed location. From there, the disturbances are going to grow in time if I keep measuring it. But then, do we see such a thing at all? We see eventually some disturbance growth and then that is thrown out. That is exactly what we are seeing in the blob body wake, right. What Nishioka and Sato said, that if you are looking at it, that location that we are talking about, upstream of which, if I look at it in this direction, then we have absolute instability, and downstream of which we have convective instability. So, in a sense that kind of sort of explains what you see. And what was Koch proposing in his work is that at this location you are getting the thing started because of some resonance mechanism. That is a resonance model. Okay. So, I suppose this is what happens, what people have looked at. Now, let me also add to what happens, that okay, we have a Kalman vortex shedding, fine. Now, suppose we decide to increase the Reynolds number further, then what we are going to study? Then that particular flow itself could be susceptible to background disturbances and suffer instability. That instability analysis is done by what was proposed by Floquet. You can see this book by Bender and Orszag that talks about instability of a time periodic system. It is a fairly decent way of looking at many time dependent systems in electrical engineering, when you are studying instability via ODEs, right. Now, if you get time periodic state, that state itself could be susceptible to further instabilities, and that is what is done. This possibility of multiple bifurcation was mentioned in Drazin and Reed, who stated that if we take a more complete model of hydrodynamic stability, we shall see that there may be further bifurcations from this solution. That is where the next least stable mode of the basic flow becomes unstable. That is precisely what I am talking about. That suppose I miss the bus here, I still have A equal to 0, I can latch on to here, and that is what is being said here, that at a subsequently later higher value of parameter, that A equal to 0 would be again susceptible to instabilities, and then you can get higher order instabilities. Okay. To the knowledge of some of us, we do not see if there are any theoretical analysis that has actually shown multiple bifurcation. This model was not studied till very recently. We did propose some multiple hub bifurcation model. Okay. So, that depended totally upon numerical simulation of two-dimensional Navier-Stokes equation. We actually use stream function vorticity formulation because of its inherent accuracy. The accuracy of the solution, one of the factor I told, is about dispersion relation preservation. In addition, also what we need to do is we need to see certain conservation principles are also followed very, very carefully. Conservation principle of what? Conservation of mass. If I solve, say, the Navier-Stokes equation in primitive variable, you know that it takes a lot of effort to preserve the mass conservation correctly. That actually is quite time consuming. The moment you use stream function as a dependent variable, you obviate the need for satisfying mass conservation. It automatically analytically satisfies everywhere. And since we are looking at vorticity dynamics, so studying vorticity itself as the other parameter is a very attractive one, and we do see the point. Okay. When we solve that equation, the nonlinear convection terms have to be sort of discretized using dispersion relation preservation methods, which provides actually near spectral accuracy. Okay. And we have this accuracy so much high that we can do calculations with very few points in azimuthal directions as well as in the wall normal directions. And the loads, the lift and drag and the pitching moment are obtained by solving the Poisson equation for total pressure. Now, what is the Poisson equation for total pressure? It is nothing but that same energy equation that we wrote it down. So, basically what happens in many of the calculations, those are reported in the literature, people do talk about solution of Navier-Stokes equation, which satisfies mass and momentum conservation. Theoretically speaking, satisfaction of mass and momentum for incompressible flow guarantees a satisfaction of the energy analytically, but when I do it numerically, there is no such guarantee. However, when you actually calculate the load by solving the Poisson equation for total pressure, that is nothing but a statement of energy conservation. So, basically in this approach, what we are doing, we are in a sense also satisfying energy conservation, and this is something that needs to be fairly well understood. Now, this part will not talk about this equilibrium time, etc., but this what we need to find out is let us talk about this multiple hub bifurcation feature that we are talking about. That is what we will come to shortly. We will show you the actual figure. If we plot A versus RE, we expect a parabolic variation as given by that equation I explained, if it was true. If it was dominated by a single mode and single bifurcation, we should get a single parabola. But suppose there are multiple bifurcations, then what happens? I will show you if I have this figure. Yeah, here we have the figure. This is what we get. If we do numerical simulation and put in also a sort of a correlation that was proposed by Norberg, shown by the dotted line. This is what we get when we actually numerically solve Navier-Stokes equation. These discrete points are computed solutions. Okay. And what we are seeing here is basically three different qualitative parabolas. Like this later part, as if I would analytically continue, it goes and hits the axis here. There is the second part which is there, and there is this part. Well, how do you know there are three parts? You see those kinks. We are noticing there are two such kinks. So, we are saying that okay, this could be the first bifurcation meeting the second bifurcation somewhere here, and this is the meeting point of the second and third bifurcation. So, this is an example where you can see it is very much there inbuilt in your governing equation, Navier-Stokes equation, And what you find is a very, very interesting thing. The first Hopf bifurcation, according to the numerical method we have chosen, that indicates a critical Reynolds number of about 52. The second one is about 64, the third one is about 85. Now, what I can talk about here is that these calculations are done without any background disturbances. The moment we add background disturbance, we could actually bring it further down. So, this is something that we should keep in mind, that multiple Hopf bifurcation is not really a figment of imagination. So, what we try to do actually, if you are interested, it is some kind of a empirical modeling. What we try to do is try to fit in a curve AE as a function of epsilon. Epsilon is the departure of the current RE from the RE critical, and this we try to do it in terms of a higher order polynomial, and you can try to fix those constants k1, k2, k3, k4. And what we have done, we have seen in that figure that we have 3 different distinct parabolas. So, in these 3 different loops, we could actually obtain this multiplicative coefficients, and this is what we get. By and large, what you can notice is basically what are these. This is like your cubic and quartic term, because you see they have been magnified 10 to the power 8 times. So, what it shows that even though you are trying to fit in a higher order polynomial, this dependence on cubic and quartic is rather weak. So, essentially what you are seeing is basically the original model which was supported by Landau, that we should have a parabolic variation, but it is only, the fact is there are 3 different parabolas in this range. The first parabola, this is the range of validity of the second, and this is the third one. I think I will just stop here. We will pick up from this point onwards and see the other aspects of blood body flows.